Masking and auditory filters. Masking and auditory filters, forward, backward, simultaneous masking, mask threshold, narrowband versus broadband noise, basilar membrane, auditory filters, critical bands, ERB, maybe MPE coding, I don't think so, masking exercise. The concept of masking. Okay, we have simultaneous masking, forward masking, backward masking, auditory filters, and relation of masking to the inner ear. Yeah, that's the point. Masking communication, basic communication model. We have some speech production, and then we have a channel with acoustic channel with noise, and we have a speech perception. Speech production channel, acoustics, speech production, acoustics, and then speech perception. Okay, recap. We have outer ear with its acoustic kind of system, the mechanical system with the middle ear with the ossicles, and the inner ear with the cochlea, and also the semicircular canals. And we have the electrical systems with the auditory nerves. In the basilar membrane and the inner hair cells, they transduce mechanics to electric impulses. Yeah, and we have yes, okay, and at the basilar membrane is each certain frequencies belongs to certain places at the basilar membrane, and they also what's called different high frequencies are near the base, and low frequency near the apex. Yeah, so there's also a frequency selectivity going on in this basilar membrane. Complicated stuff in itself. We have the hearing thresholds with the hearing threshold curve, and it has minimum at about 3,500 hertz where the resonance frequency conditions are 2 years, normal hearing, 18 to 25 years old, and one tone at a time, so on. Yeah, 2 years, free field, no background noise. Then we have simultaneous masking. Okay, we have some power, integral of power, spectral density, that's a power. For white noise, white bandwidth B in hertz, big L white noise is sound level in dB, small l white noise is spectral level. If dB is a decibel in SPL per hertz. So the sound level is sum of the spectral level plus 10 times the 10 logarithm of the bandwidth. For instance, if you have a spectral level of 30 dBs and a bandwidth of 100 Hertz, then the sound level will be 30 dBs plus 10 times logarithm to 100, and that gives 50 dBs SPL, and so on. We have some tone in broadband white noise, tone in broadband white noise, and we have the mask thresholds for broadband. It shows up that if you have a spectral density, a spectral level is called, I think it's spectral level, about 25 dBs. Okay, then there's some masking going on, and yeah, white noise. We're talking about white noise masking. If the frequency is lower than 500 Hertz frequency of the signal, then there is a constant threshold. But if it's more than 500 Hertz, this tone, then the masking will increase 10 dBs per decade, or it means about, I think it was 3 dBs per octave. If you go from 1000 Hz to 2000 Hz, the masking threshold is 3 decibels bigger. Yeah, as we have the threshold, boom, and then yeah. For fixed frequency, masking threshold increases linearly with spectrum level of masker. Yeah. For fixed frequency, MT increases linearly with spectrum level of masker. Yeah. 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 Boom boom. Yeah. Boom boom. Yes. Okay. Frequency dependence of narrowband noise. We're still talking about simultaneous masking. Then the frequency of the dependence of narrowband noise is different. It shows up that if you have a frequency of test tone in first axis and it is logarithmic build up, yes, yes, then the shape of the masking curve are almost the same. Even if you use maskers as 250 Hz or 1 kilohertz or 4 kilohertz. Yeah. Yes. Yeah. So yeah, if the frequency, if the masking tone and the frequency, the masking frequency and the tone frequency are the same as a big masking. If the tone frequency is deviating from the masking frequency, the levels, masking level is going, threshold is going down. Yeah. Yeah. Okay. Observation: shape of masking curves almost independent of masker frequency when plotted on log frag axis. So then you have the so-called the concept mask threshold for narrowband noise, upward spread of masking. If you increase the masking level, then there is a so-called upward spread of masking at higher frequencies. As I told you, if the signal frequency is the same as a masking frequency, there's a big mask. If the frequencies for the signal are more than the masker frequency, there's a upward spread of level. You can say for higher frequencies, signal frequency than lower frequencies. Also signal frequencies lower than the masking frequencies. Yeah. And this tendency of what masking frequency is increasing with the masking when the masking level is increased. Then we have non-simultaneous masking. We can have forward masking. You have a noise masker in front of us before a signal. In test pulse, it could be a Gauss test pulse is called sometimes. Masking can still be observed even when the masker and signal are not present simultaneously. Okay, noise burst precedes the signal. Count the number of steps and you can hear the signal preceding the noise. It shows up then when the time gap is very close, is when the test pulse is very close to the noise masker. When it stops, then you need a big signal. When the time gap is bigger, then you need a smaller signal to overcome the masking. Threshold of a short Gaussian pulse as a function of the gap duration after onset of a masker. It shows up that if the delta t is about 200 milliseconds, then up to 200 milliseconds there is an impact. After 200 milliseconds, the masker don't have any impact on the signal anymore. Backwards masking is when the signal is coming in before the masker, but even then there is a masking. Signal is followed by a noise burst with a brief time gap in between. It is heard alternating with a noise burst alone. Count the number of steps you can hear, blah 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 blah. You have a test pulse before the masking, and the closer the test pulse is to the beginning of the noise masker, the more signal you need. But of course, this time gap is not 200 milliseconds. The gap duration is 20 milliseconds. Yeah. Yeah. Yes. So yes. So when after 20 milliseconds, if the signals is before 20 milliseconds before the noise masker, the noise masking has no impact. Yeah. You can also have partial masking because yes, not some of the if one sound doesn't mask another sound completely, we talk about partial masking. Influence on the loudness of the sound decrease in loudness, of course. We know it. I think we know it from the daily environments. Some masking noise, but not totally. Auditory filters. Why do these filters look that way? We have the inner ear. We have the organ of Corti and the cochlea with the three liquid containers, scala vestibula, vestibuli, scala media, and scala tympani. We have the basilar membrane in between media and tympani, and there's a frequency. Basilar membrane is a frequency analyzer. If you have some tone with different frequencies, a sound with different frequencies, then there's a frequency selectivity going on the membrane. The high frequencies are near the base, near the oval window, and the smaller frequencies, lower frequencies, are near the apex. Yes. Yep, that's it. Okay, and we have some auditory filters, auditory filter bank. Auditory filters are the kind of way to explain what is going on by these frequency selectivities. You have some center frequencies, and your bigger center frequency, the broader are the auditory filters. So you can see a tone when it comes to the basilar membrane at a certain place. There's some there's some frequency selectivity going on, and yes, and make some auditory filters. Yeah. Yep. Then we have some characteristic of a bandpass filter. Center frequency F0, bandwidth, and usually taken as a range of frequencies with response within 3 dBs of peak. And then we have a quality factor F divine bandwidth. Thank you.